Hello and welcome everyone. We're happy that we're all together again. In this tutorial, we will start arranging all the steps that we have illustrated before and some steps to make any solar system design. Are you ready? Fasten your belt and let's get started. The aim of this tutorial is to understand some general steps you must follow to make your solar system design, and we will represent those steps in some forms of a practical example. So let's go ahead. The first step we have in the design is to detect the coordination of the place we are making the solar design at which. So those coordinations are represented by the place latitude and longitude. And for example, we suppose we are making a design in New York. So to get the coordinations of New York or of any location in the world, there is some beautiful online websites that you can use for this purpose. Now one of them is called the latlong.net. So this is its hyperlink and here we can check it. As you see, this is the website and all what we need to do is to type the location name in this bar. Then its coordination will appear to you. So let's type, for example, New York. And press enter. Here it appears that its coordination is 40 for the latitude and minus 74 for the longitude. So let's go back. That's good. After getting the latitude and the longitude, the next step is to get the tilt angle theta, that is the installing angle of the panels on the ground. And as we learned before, theta equals 90 minus the elevation angle, but the elevation angle is still unknown now. So for alpha, it's equal 90 minus the latitude plus the declination angle. So we just have calculated the latitude, but we need to calculate the declination angle itself. So this is the declination angle formula, and we knew that it depends mainly on the day number on the year that we need to detect the Earth declination at which. Now we need to select the day that has the worst solar radiation in the year. And this is because we must make our design on the worst case, because if we made the design on the worst case, the design at this condition will be able to cope any other cases. But if we made the design on the best case, at this condition when the solar radiation becomes fewer at any day, this will give us a smaller output electrical power that will not be sufficient to feed the electrical loads. So by selecting the worst case, we can increase the number of solar panels to get the required output power. But we know also that the worst radiation in the year is coming at 21 of December. So when searching the days table, we will find that this is 21 December, and here this is the intersection that gives us a day number of 355. Now when substituting by this 355 to get the declination angle, it will be minus 23.5. So this is the worst declination angle in the world that gives the worst solar radiation. So when substituting back in the elevation angle, it will be 26.5, and then when substituting back in the theta, it will be 63.5. But as we said before, the tilt angle has some standard values according to the manufacturing standards, so the nearest standard to it is 60 degrees. So this is the second step required, which is the installing angle of the panels. Now the third step is to get the S sub m, or the peaks and hours, and to get it we must firstly calculate it for each single month separately. As we know, the solar radiation differs from one month to the other, so we will firstly calculate it each month. So S sub m depends on the global horizontal radiation, so we must calculate S sub h each month. And this value, S sub h, is a given value that some scientific organizations are collecting, so the S sub h is detected at each point on the Earth. So we will get it from the NASA database, as NASA provides us with a global horizontal radiation values for each coordination on the Earth. So what we just need to know is the location, latitude, and the longitude that we just have got, and then enter the NASA database, then get the value of S sub h each month. Now this value for each month is the average of the month's day, as the average of the month day is. As we know, each day of the month has a different value of S sub h. So this value that we will get as the average value for each month. Now the second thing we need for getting the S sub m is the tilt angle theta. But as it's a constant value, so we will use it to be a fixed angle that we got. Also, we will get the declination angle at 21 December, and then we need to get the elevation angle that depends on the declination angle, and we got it at 21 December. Now, after getting S sub h, beta, and alpha, we are ready to get Sm. But you know, this is an approximate assumption to get alpha at only one day in the month, which is 21 December. And the most accurate solution is to get alpha each day in the month, then we get the peaks and hours each day, and after that we get the average of all days in the month to get each month peaks and hours. But for now we will try this assumption as it's more simpler in the calculations, and later we can try the accurate solution by getting S sub m each day in the month. Now we need to get S sub m each month, so we must calculate it 12 times, but for the illustration purpose, we will take two examples for January and February. So those are the global horizontal irradiation for New York each month, and here it's a screenshot from the values that we need. Here for January, the S sub h equals 1.97 hours, then beta equals 60, and the declination at 21 of January, so the day number is 21, then it will be minus 20.1 degree. Now the elevation angle of 21 January is 90 minus the latitude, which is 40, plus the declination angle, which is minus 20.1, so alpha equals 29.9 degree. And finally, we get the S sub m to be S sub h times sine alpha plus beta over sine alpha. So it's equal 3.95 hours. Now let's repeat those steps fast for February. Here S sub h equals 2.86 hours, then beta equals 60, and the declination angle for 21 February equal minus 11.2, then alpha equal 38.3 degree. So the global tilted irradiation at this condition equals 4.5 hours. That's great. Now we will do the same thing for the rest of the 12 months, and for this we have prepared all the required values for the 12 months. So those are the required parameters at each month. Here we have S sub h given from the database of NASA, then beta is a fixed value at all of the design, then the declination angle is determined at 21 of each month, and alpha is determined each month also according to the declination. Then S sub m is determined each month according to the above data. And finally, we get the average value of all of the months of S sub m. But you can ask, will we take the average value of the S sub m to be the global tilted irradiation or the final value of the global tilted irradiation? So this depends mainly on something. Here, the difference between the maximum value we got for S sub m and the minimum value is greater than 2 hours. So if the difference is greater than 2 hours, we will choose S sub m to be the minimum. And if the difference between them is less than 2 hours, we will choose it to be the average value of all of the months. And here for our case, the minimum value is 3.86 and the maximum value is 5.38. So the difference between them is 1.5 hours, which is less than 2 hours. And for this condition, we will choose the average value, which is the summation of all the months' value over 12. So it will be 4.6 hour, which is the final value of the global tilted irradiation hours. So by this way, we can get the final value of the net hours at which we will get a maximum radiation from the solar panels, then the maximum electrical power that we need to feed our loads with it. So at this point we have finished. Hope that's clear right now. Thank you for watching and see you next tutorials.